next speaker of the day is Elisabetta Vallarino from the University of Genova, and she's going to talk about the impact of spectral complexity on estimating source space connectivity from EMG data. So please, Elisabetta, the stage is yours.
Thanks, Sarah, for your introduction. Today I'm going to talk about the impact of spectral complexity on estimating source space connectivity from MEG data. And in particular, I will focus on the impact of the spectral complexity on the choice of the regularization parameter when using minimum norm estimate to estimate the neural activity. First of all, I want to thank Sara Somariva, Michele Piana, and Alberto Sorrentino, who worked with me on this project. So let's start with an overview of the problem. We are dealing with MEG recordings, so we are dealing with the recordings of the magnetic fields outside the head produced by the neural current that flow inside the brain. And our aim is to estimate brain source space functional connectivity at our best. And to do so, we typically proceed with the two-step process. So in a first step, we estimate the neural activity given the MEG recordings, and then from the estimated neural activity, we proceed with the computation of functional connectivity. During the first step, the MEG inverse problem has to be solved. And of course, you all know that there are plenty of methods at our disposal, but in this work, I focused on minimum norm estimate, where a regularization parameter needs to be set. We call this parameter lambda. Today, the fact that I want to show you is that the spectral properties of the neural activity influence the parameter providing the best estimate of functional connectivity. So, from a mathematical viewpoint, we are dealing with the linear inverse with a linear problem, where X is a multivariate stochastic process that models the activity of n sources in the brain, while G is the forward model that is called the lead field matrix, as you all know, and N is a wide Gaussian process that mimics the measurement noise. And finally, Y is the MEG recordings provided by M sensors of the instrument. And as I said, we are interested in estimated functional connectivity. So we need to set a connectivity matrix, and given the connectivity metric, so the connectivity metric is a one-parameter family of matrices of dimensions n times n, so number of sources in the brain times number of sources, and the parameter is f. That is the frequency in which we compute the connectivity metric. So as I said at the beginning, functional connectivity is usually estimated in a two-step process. So first, we compute a regularized estimate of the neural activity. And in this work, I focused on the minimum norm estimate method. With this method, the neural activity, the regularized neural activity has this form, where lambda is a proper regularization parameter that trades off that is the trade-off between fitting the data, between fitting the data and mitigating the impact of measurement noise. Once we computed the regularized estimate of the neural activity, we proceed with the estimate of functional connectivity. So it arises the question of how to properly set the regularization parameter lambda during the first step in order to obtain the best possible estimate of functional connectivity. And And the question is the parameter that provides the best estimate of neural activity also the same that provides the best estimate of functional connectivity, or should we set a different parameter if we want to estimate functional connectivity? And this problem has already been investigated in literature. I want to point out these two works. So the first one is from Incapié and others. In this work, the minimum norm estimate has been used as an inverse method, and the authors in this work they work in a simulation framework where they simulated the neural activity using sinusoidal time courses, and they focused on the parameters providing the best estimate of coherence and the best estimate of the power spectrum. So in this case, the coherence is of course a measure of connectivity, while the power spectrum is, so they basically just consider the diagonal elements of the cross power spectrum. So no interaction were considered with this. And what they found is that the parameter providing the best estimate of coherence is about 2 orders of magnitude lower than the parameter providing the best estimate of the power spectrum. We need to regularize less if we want to estimate connectivity. And also in a previous work that we did, we investigated the same problem in an analytical way. So we considered minimum norm estimates as inverse method, and we assumed that both the neural activity and the measurement noise were wide Gaussian processes. Of course, this is a strong assumption for the neural activity, but it was needed to proceed with the analytical computation of the parameters, of the optimal parameters. What we were able to find is a closed formula for the parameter providing the best estimate of the neural activity, which is given by this formula. So basically, we have the variance of the noise over the variance of the neural activity, which is basically 1 over the SNR, which is a classical result. And most importantly, we were able to find this relation between the parameter providing the best estimate for the cross power spectrum and the one providing the best estimate of the neural activity. And even in this case, we see that less regularization is needed if the final aim is to investigate, to study the functional connectivity. So schematically, the point is this. So from a sensor data, so from our MEG data, we have 2 options. So one is to set the parameter in order to optimally estimate the neural activity, but then with this choice, we don't get the best estimate of functional connectivity. Whereas if we want to optimally estimate functional connectivity, we should set a different parameter, or better, a smaller parameter. And in this case, we don't get, an optimal estimate of neural activity. So in the work that I want to present you today, we went further in the investigation of this problem, and we also wanted to see how the spectral properties of the signals that describe brain activity influence the parameter providing the best estimate of functional connectivity. And as connectivity metric, we focused again on the cross power spectrum, with the idea that from the cross power spectrum, many other connectivity metrics can be computed. And we proceeded with the numerical simulations to investigate the role of spectral complexity. Okay, so now before showing you the results, we need some definitions. So first of all, we need to define who the optimal parameters we are talking about are. So we define the two optimal parameters, lambda x for the neural activity estimation and lambda s for the cross power spectrum estimation. And they are defined as the two values that minimize what we call the reconstruction errors, that are these two here. And they basically are a normalized L2 norm of the difference between the regularized, so the estimated neural activity and cross power spectrum, and the actual ones. Okay, then we also need to define the spectral complexity. So the idea of spectral complexity is that the more complex the relations between the signals, the brain signals are, the more the more is the spectral complexity. And to quantify the spectral complexity, we used this spectral complexity coefficient, which is defined by this formula. So basically what we did is we consider all the matrices of all the cross power spectra matrices, and we compute the L2 norm over the frequencies. And then in this way, we obtain a squared matrix, and we average the upper part of this matrix, just the upper part because it's symmetric. And you can see here in the plot that to higher values of the spectral complexity coefficient correspond a more peaked spectrum. So the idea is that the higher these values, the more complex the relations between the signals are. Finally, we also need to define the signal-to-noise ratios. So we recall the models we are dealing with. So the linear model, the MEG linear model, and we also have this second linear model, which is obtained by computing the cross power spectrum of this first model of both sides of the equation. And so these models directly links the cross power spectrum at source level with the cross power spectrum at sensor level. Now, with these two models in mind, we can define first the SNR of X, using the classical definition of signal-to-noise ratio applied to the first equation. And then in a similar way, we define the SNR of S using the same definition, but this time applied to the second equation. All right, so now we have all the definition that we need. Now, as I told you, we work in a simulation context, and this is the sketch of the simulations that we did. So starting from here, we simulated several pairs of neural time courses, and with different spectral complexity coefficients. Each of these pair, and they followed a multivariate autoregressive model. Then each pair of time courses was assigned to a pair of point-like sources within the brain. So the brain activity is comprised two active point-like sources, while all the other sources were set to have null activity. Then the simulated neural activity was projected to sensor level using the Lidfield matrix. And then we added sensor noise with different intensity levels. So in this way, we simulated several pairs of time courses, different positions for the active sources, and different level of sensor noise. In this way, we generated 1,200 different sensor level configurations. Then for each of these configurations, we proceeded with the first step. So we estimated with minimum norm estimate the neural activity. And then we estimated the cross power spectrum. And then we numerically computed the optimal parameters, lambda x and lambda s. And to do so, we minimized the reconstruction errors that I defined a couple of slides earlier. So, so basically for each configuration, we end up with a pair of optimal parameters. Now, let's see what the results that we obtained. So this plot summarizes all the results. So in the Y line, the vertical line, you see the ratio between the two parameters, lambda s and lambda x, versus the SNR of x. And first we see that the ratio between the two parameters is always lower than 1, or better, is lower than a half, much lower actually. Meaning that less regularization is needed to, if we want to optimally reconstruct the cross power spectrum. But we also see, okay, different lines here, different colors here corresponds to pair of parameters coming from pairs of signals with different spectral complexity coefficients. And you see that the lines are ordered from the top to the bottom for increasing spectral complexity. Meaning that for increasing level of spectral complexity coefficients, we need to regularize even less to obtain the optimal reconstruction of the cross power spectrum. Now, to better understand this result, we can have a look at these two plots. So in these two plots, lambda s is plotted versus here versus the SNR of x, and here versus the SNR of x, of s, sorry. And while, while in this plot, the lines do not overlap, but they are ordered like in the plot that I showed you before, from the top to the bottom for increasing spectral complexity. In this plot, the lines overlap. So this suggests that somehow the definition of spectral complexity is included in the definition of SNR of S. And indeed, it is like this. Okay, we can now have a look at this relation that relates the SNR of X with the SNR of S. Now, to get to this relation, just we see quickly how to get to this relation. So we recall the definitions of SNR of S, of X, and SNR of S. And we also recall that we assumed at the beginning that the measurement noise is a wide Gaussian process with the covariance matrix alpha squared times the identity. So in this case, these two equalities hold. Now, if we substitute these two terms that appear in the definitions of the SNR, in the definition of signal to noise ratios. So if we substitute, we obtain, of course, this, and we can isolate alpha squared from here, and we can substitute it in here. And with a little bit of calcula, we get to the first relation that I showed you. So now this was just to show you how to get to this. But now let's focus again on this relation, and in particular, we now focus on this quantity, where it appears the cross power spectrum at source level. And this quantity gets higher for increasing level of the spectral complexity coefficient. So what we have is that for same level of the SNR of X, we have higher values of the SNR of S for increasing values of the spectral complexity coefficients. And this explains the first plot that I showed you before, because, okay, for higher values of the SNR of S, we need to regularize less. So basically, for same levels of the SNR of S, the SNR of S gets higher for higher values of the spectral complexity coefficients, and thus we need to regularize less. And this, as I said, explains the first plot in which we see that, okay, maybe I can show you it again, where we saw that less regularization is needed for increasing values of the spectral complexity coefficient. Okay, this is the first result that I want to show you, that I wanted to show you today. But I also want to show you some preliminary results that we are obtaining. So we are, so the idea here is that we want to further investigate this problem of setting the regularization parameter when we want to estimate functional connectivity. And we wanted to do so in a more complex framework and with the other connectivity metrics other than the cross-power spectrum. This is a work that has just begun in collaboration with Karin Gerbi, Anna-Sofia Encapié, and Annalisa Pascarella. So I will go through it very quickly. The idea is that we are now simulating, okay, the pipeline of the simulation is basically the same, but this time we are simulating more complex brain activity. So we are not dealing with the point-like sources anymore, but we are working with patches, and we are adding also some background noise to the sources that are not in the patches. And we are also computing several connectivity metrics. The cross-power spectrum, imaginary part of coherence, corrected imaginary phase locking value, and weighted phase lag index. And so we are always generating several sensor level configuration, and for each configuration we compute the optimal parameters for the neural activity reconstruction and for all these connectivity metrics. And in this case, the optimal parameters are defined as the ones that maximize the area under the curve. So here, the results that we are obtaining. So in this plot, the different panels correspond to the different connectivity metrics we are considering, and on the X-line, there's the ratio between the parameter that we are testing and the optimal parameter for the neural activity reconstruction. So the red line corresponds to 1, which is the parameter for which corresponds to the optimal parameter for the neural activity reconstruction. And you see that the higher level of the AUC is, that corresponds to the parameter providing the best estimate of the neural activity, of the functional connectivity, is always about 2 orders of magnitude lower than the one providing the best estimate of the neural activity. Meaning that we need regularization if we want to investigate functional connectivity. And finally, this is just to show you a representation in the brain to see how better the reconstruction are if we actually set a smaller parameter. So this is just one realization of MEG data and just one of the connectivity metrics that we are testing. But here you see where the patches that we are simulating are, and we are computing seed-based connectivity. So we compute connectivity from the seed, which in this case is this one, to the target that is this one. And so here is the ground truth that we the ground truth where the connectivity that we want to detect is this one. And here you see the reconstruction of the phase lag index that we would obtain if we use the optimal parameter for the neural activity reconstruction, where here you see the reconstruction that we get if we use the optimal parameter that we found that it is about two order of magnitude lower than lambda x. And you see that here the reconstruction is much more localized, while here is very spread. So to conclude, we saw that the spectral complexity influence the parameter providing the optimal reconstruction of the cross-power spectrum. And we also keep seeing that a smaller parameter should be set to estimate functional connectivity. We now have many confirmation of this. So this would be like the take-home message. And now, of course, future direction for this work would be, and this is actually our what we are working on now, is to implement a learning algorithm that infer the optimal parameter for connectivity estimation, exploiting all the features that we can extract. And of course, the first of these features would be the spectral properties of the neural activity. And also one thing that can be that would be interesting to do is to implement a one-step approach to estimate functional connectivity in order to directly estimate functional connectivity from the MEG data without going through the reconstruction of the neural activity. And okay, with this I'm done. I thank you for the attention.
Thank you very much, Elisabetta, for this nice talk. I think we have time again just for one quick question. Let me see if there are any from the audience. Okay, one question from Annalisa.
Hi, Elisabetta.
Hi.
Okay. Congratulations, very nice talk. And I have a question more theoretical. Okay, so did you find the relation between the two regularization parameters in case of connectivity metrics? And you think that you can easily generalize also exploiting the relation that this morning Nolt explained?
Sorry, you mean?
Yes, the relation between
yeah.
two regulation parameters.
Mm-hmm.
So you found for one case and all.
No, yeah. I just found it for the cross-power spectrum, and just for the case, like the analytical relation was just for the case where the neural activity was assumed to be a wide Gaussian process. Otherwise, also for the cross-power spectrum, it gets complicated, and so I imagine that for the other connectivity metrics, it's also complicated. But we haven't tried.
Okay, thanks. And another question: how did you compute the optimal regularization parameter in the last?
Here, yes. So in this preliminary results. so we are testing several values of parameters, starting from the optimal parameter for the neural activity reconstruction. So we selected a range of parameters centered in the optimal parameter for the neural activity, and then we computed the area under the curve by computing the active and the negative sources, considering different threshold levels.
Okay,
I don't know if this answers the questions.
Okay. Thanks a lot.
We have maybe a question from Roberto Guidotti. Yeah, okay.
Hi, maybe it's a silly one, but just to clarify myself, I was a little bit, I paid attention on the last sentence that you said in order to have like a one-shot connectivity estimation. Is this a possible application on real-time connectivity estimation, or did I misunderstood something?
All right, I have no experience in the real-time connectivity estimation. I'd say there are some computational issues because we are dealing with with very big matrices in this case, because so it would be something like, the relation would be something like this. So the idea is, for example, for the cross-power spectrum to directly estimate the cross-power spectrum of source level from the one at sensor level. But of course, we are dealing with very high dimensions that could, that could be hard to manage in real time, I'd say. But I have no experience with the real time things. So
and also, since we are using the spectrum of the data, so anyway, you have to have enough data to have a good estimate.
Yeah, sure. Yeah.
Okay. So it's not actually, maybe not in this form. I'm not sure it's gonna be okay for real time analysis.
Yeah.
Okay, thank you.
Okay, so thank you again, Elisabetta, and a virtual clap also for you.